today. Now, one thing I'd like to clarify for a lot of people in the audience who are seeing this stuff for the first time, and you look at the slide and you'll see we're part of the National Weather Service. And people tend to, in this country, tend to say, why is space weather doing in the National Weather Service? Why is it not NASA? And I'd like to point that out just because it's a reflection of where this issue of space weather has come today, because indeed we were more of a researchy, geeky type of group back in 10, 15 years ago. But as we became more and more dependent on this advanced technologies for everything we do today, we recognized that space weather was a real threat. A real and current threat on that very technology that we rely on. So no longer did we belong in any kind of a researchy entity or a researchy agency. We belonged in an organization that issues alerts and warnings, and that's what we do. We issue the alerts and warnings like any weather station in the National Weather Service, except I don't really care about the tornadoes and the hurricanes, the blizzards and whatnot. My interests lie way above that, on the solar flares, geomagnetic storms, and radiation storms, and how it can affect that technology. So in the Space Weather Forecast Center, and you're very welcome out to Boulder if anyone's ever interested in coming out. Don't come on a day like today or yesterday where it was 15 below zero when I left Boulder yesterday morning. But we have an operations center there, staffed 24/7, providing alerts and warnings for the nation, and indeed our colleagues around the world. What I wanted to hit on today is a little bit about the solar cycle business. Sometimes it's somewhat misleading and misunderstood. And close calls, a couple of key messages that I want to make sure when you walk out of here today you understand some of these key messages, so I'll highlight them. And some of the impacts, just some of the more rubber meets the road type stuff, because I know there's folks out there that hear about this space weather stuff and they just quite don't get why it applies to them and whatnot. I hope I can leave you with some kind of understanding why one should care about it. This chart here, and I know from the folks in the back it's busy, it's supposed to be busy. What it is the reflection of what happened back in October, it's 10 years ago, October 2003. We refer to them as Halloween storms. This was the wake-up call. It was at this point in time that we really realized, we've had some activity in the past that did cause problems, but the widespread and diverse impacts of this period of time in late October was the wake-up call. We recognized, hey, when we don't have GPS, that's not a good thing. If we don't have GPS for a few minutes, it's not a good thing for some people, but if we should lose it for days upon end or longer, it would be very, very significant. Any kind of satellite communications, and of course, as everyone is aware in this audience, we have concerns with our electric power grid, but you can just see across the world, and it's one of the takeaways from this slide, is recognized probably like no other natural phenomena. These big space weather storms are global. They're not going to focus in on one area. There will be localized effects and whatnot, but we could be seeing power grid problems in Canada or in the northeastern United States, and at the same time, the ESCOM network in South Africa could be having significant problems. It is a global phenomenon. I wanted to talk a little bit about the solar cycle, and I'll key in on the takeaways here. When you look at this plot, you'll just see that graph, the blue line back in the horizontal scale in the bottom's the year. We had our last solar maximum in 2000 and 2001. We're ramping up into this next maximum. It's an 11-year cycle, and for folks who don't understand, when we talk about a solar 11-year cycle, it's simply the Earth, or the sun is like the Earth, in the sense that it has a North Pole and a South Pole, a magnet. A negative and a positive polarity, but the sun does something a little weird. Over 11 years, it does a polarity reversal. Earth does not do that, obviously, and it's during the course of this polarity reversal when the magnetic field lines on the sun get so twisted and distorted, and they push out, and the actual visible piece of that is sunspots. When we see sunspots, like a meteorology sees a low pressure area, that's our low pressure, that's our nor'easter, when we see these big sunspot clusters. So that's what the solar cycle is, and we got a period when you look on the left-hand side, that big up around 125, we're measuring the sunspots every month. And then things quieten down as the magnetic fields get settled and they ramp up again. Now, so first key takeaway here is this. If you look at the next cycle, we were predicting it was the red line, ain't gonna happen. It's gonna be a small cycle, and perhaps the smallest cycle in the last 100 years. So unfortunately, some folks get the wrong message there and suggest that this suggests that perhaps we're not going to see any significant activity for the next 2 years or 5 years or 10 years. Not the case at all, and I'll just show you why that is. If you look at this plot this is a plot of 250 years of solar cycles. And I'm going to key in on two of the particular cycles, 1859 and 1921, and I know that will resonate with some people in this audience. The red dashed horizontal line is average cycles. I'm pointing out those two cycles in 1829 and 1921 because both of those cycles were smaller than average, and that's when the big ones occurred. The big space weather events occurred. The biggest, when we talk about that Carrington event in 1859 and the potential consequence in the nation today, that occurred in 1859 with a smaller than average solar cycle. So the takeaways here, I don't care about the solar cycle. Yes, we're going to see less activity if I have less sunspots, but that big one could emerge, isolated, rogue in nature, but it could sit there and produce that significant event. So do not dismiss space weather because it's a lower solar cycle. It's interesting, people say, how do you guys know about 1859? We actually had the technology back then to measure the magnetic field of Earth. So that video green plot you see there is from an obscure observatory of the magnetic field in 1859. So we actually have the records to see how strong the storm was. The 1921 storm is interesting. I'm a bit of a history buff, so I like looking back at the New York Times and some of the other publications because, needless to say, we talk about our reliance on the advanced technologies today. Well, in 1921, they talked about their reliance on the advanced technologies of that day. And indeed, even in 1921, space weather impacted the technologies of that day. And if you look in the article on the left-hand side, where it's out of the New York Times, and it'll tell you that when the big geomagnetic storm in 1921 occurred, it said that the entire signal and switching system of the New York Central Railroad below 125th Street put out of operation, followed by a fire in the control tower due to the induced currents. So we've understood this phenomenon of space weather for quite some time because it's always had some impact on technology, but of course today we're concerned it would have a tremendous impact on technology. Now that's kind of just difficult again to see in the back, but let me tell you what this is, and it's always interesting. Our folks in Canada, Alaska, understand the Northern Lights. We see it quite regularly up there. Imagine what the folks in Cuba thought on that September morning in 1921 when they saw the aurora right before sunrise. That's how intense this magnetic storm was that the beautiful aurora borealis was visible in Cuba, Hawaii, and other places. Now, when I mentioned dodging the bullet, this is a really important message to take away here. When we talk about this Carrington event in 1921 or 1859, I tell people Carrington events occur every 11-year solar cycle. We see some Carrington events. We see them, but the perfect storm, from their perspective, is that CME the eruption from the sun has to impact Earth. But the eruptions are occurring in the sun all the time, and this is a case in point. This was 23 July 2012, and I believe Peter Pry mentioned it in the panel discussion this morning. We were sitting there, and we're looking at the sun from the Earth side on the yellow image here. Little sunspot there about the size of the Earth, but really of no significance to us. And all of a sudden on this other image, and what you see on this other image, the blue image, is what we call a coronagraph, where we essentially create an eclipse. We're blocking out the sun with an occulting disk, and you see all that material shooting out? That is an extraordinary fast coronal mass ejection. And that got our attention real quick in the operations center, and we see something like that. Our first concern is, where the heck is it coming from on the sun? Is it the front side of the sun coming towards Earth? No, because the sun was very quiet. The sun looked like that. Fortunately, though, in the technology today, and our good friends in NASA provide a great service where we have what's called a stereo mission. Stereo by its name will give you some clue of what it is. 2 different spacecraft in orbit around the other side of the sun. So we can see all 360 degrees of the sun, which is great. So now I said, okay, let's find out where this eruption came from. That big bright area, there was a tremendous flare. And we're able to measure how fast the coronal, that material that's blasting out into space, was moving at almost 6.5 million miles an hour. So it could make the sun to Earth 93 million mile transit in about 17 or 18 hours at that speed. The Carrington event in 1859 made that 93 million mile transit in 17.6 hours. So by many, many measurements, this event that occurred in July of 2012 was Carrington-like. I don't say absolute Carrington because we don't know how it's going to couple with the Earth's magnetic field and how the induced currents will occur, but all the other stuff was there. October 2003, again on this theme of dodging the bullet, other things we've seen happen in the last 10 years that people don't realize because they hadn't had too much of an impact. These were the Halloween storms. They had impact, but it could have been much worse. We were looking at kind of a worst case scenario, and I'll tell you why. You see this big sunspot cluster there on the left-hand side of the sun. That's about 10 to 15 times the size of Earth. The sun takes a full 27-day rotation. When I see something like that, and our folks, or my friends in the forecast center see something like that, we got an issue. This is our kind of our nor'easter. But what happened over the course of the next week here, and Dana, just go ahead and click on that image, and you'll see as this goes into motion, watch what rotates around the lower left-hand side, another monster sunspot group, and watch what develops above it. Another. We had 3 nor'easters we were dealing with, all of them as big or bigger than what Carrington was looking at in 1859. If this situation should occur today, we have processes in place now to notify Craig Fugate, FEMA leadership, National Operations Center and the DHS, and National Security staff, many others in government leadership. We recognize now, we didn't back then, the threat is so great, but this was a perfect scenario. We could have got nailed. We did get considerable impact, as I showed in that first slide, globally, how it impacted Earth, but power grid came down in Malmö, Sweden, damaged transformers in South Africa. We were spared. We were lucky. We had some big events. They just weren't the extreme event, but they could have been. So, again, just to take away here that these events, these are the big events that have occurred, and we just kind of got lucky. And I just wanted to finish. That big sunspot on the lower left-hand side, as it rotated on the very right-hand side of the sun, it was about to make its exit off. It had done its damage, it had done its piece. It had one last shot for us on the 4th of November, and you'll see the image on the upper right-hand side. It was another powerful blast, and that ugly trace in the lower middle there is the X-ray emissions, and that was the biggest X-ray emission we've ever seen since we started about 40 years ago looking at these things. So that coronal mass ejection shooting out to the right, it's not Earth-directed. Again, we got lucky. So just recognize these things are happening quite regularly in the sun. Just all the ingredients have to be there, and that last ingredient is it has to be Earth-directed. Sometimes it's not. So I just wanted to touch on a couple of the space weather type impacts. A lot of people say, I just start getting this space weather stuff. So well, if I give you some idea of some of the impacts we see, you'll get some idea of why we monitor this so closely. Well, I was down in Atlanta last year visiting CNN. And the CNN folks were asking, well, Bill, how are we doing with our coverage of space weather? And I said, you do pretty good, except you get something wrong every time. So what's that? It's that every time when the storm is over and you say nothing happened, you are wrong. Things are happening all the time. People don't want to talk about it. They don't want to share it, and a lot of it is just not really sexy news stuff. But every time we have a moderate level space weather storm, because of the diverse nature of our customer base, imagine GPS. The GPS pervades society today. We have so many users, so many critical applications of GPS. We get these moderate storms, GPS users get impacted, I assure you. This is just even with the small solar cycle and not much happening, I just wanted to show you a couple of things, like in the March 2012 activity, the big light squared satellite zapped. They thought it would be out for maybe a day during the impact from that solar flare. It ended up being down for 3 weeks. The DoD don't like to talk, needless to say, too much about impacts on our classified and other sensitive systems, but you'll see in the Stars and Stripes that the general did come out and say, yeah, it interfered with the Air Force satellites. I'm not going to give you too much more info, but it will impact various systems. Aviation always gets impacted. And if you read it down here, 13 May 2013. This is a report that comes from air traffic control. We have nice relationships set up with these folks, and they give us feedback. So during that activity, and this is I know a lot of our folks in the audience here are either hams or like HF Comm operations. Solar activity causing severe impact to high-frequency communications. These people are trying to get messages to aircraft to go up, to go down, to go left, to go right, and they cannot because the space weather is impacting their ability to communicate. Again, we don't like to share this stuff. It's not stuff that's going to make the press, but it'll happen every time we have any kind of space weather activity. Another HF impact, just to show you. When we have a big solar flare, if you look at the green image and you see the big bright flash, obviously that's the solar flare. On the right-hand side, the image of the Earth shows where the high-frequency communications will be impacted. Because when the flare occurs, within 10 minutes or so of that thing happening on the sun, actually within 8 minutes, we're feeling the effect on our ability to communicate right here on Earth. And when you look at this image, and I'll put it into motion, it's a sunlit side of the Earth, and anything red is bad. Red means we've lost the capability completely. Lower frequencies would be degraded when we're in the yellows and blues. So Dana, just click on the right-hand side on that image and watch what happens. The flare goes off, and all of a sudden, across the Atlantic Pacific, HF comms within a minute are shut down. GPS gets impacted, radar systems. We get this information, the Cheyenne Mountain, into the DoD within 2 minutes. They need to know what kind of interference is impacting their radar systems and other technology. And I just wanted to show you an impact on the GPS. This was kind of a phenomenal impact and give you a good an example of what can happen during the solar flare. What you see the big flare on the image on the left-hand side, very bright, obviously. But the Earth, the map of Earth with the green dots, they are a GPS receiving network. Green is good. When it goes red, it's bad. We have this big flare. And this was actually during the solar minimum, which is why I point out space weather can occur anytime, 6 December 2006. But I'm going to put this in motion because we get this big burst. And watch what happens on the sunlit side of the Earth. When those green dots go red, go ahead, Dana, and just click on that. When they go red, we've lost that GPS capability. So you'll see the little red dot in the bottom. Things are not too bad. We're not seeing any big burst. And then all of a sudden, the spike here is the burst and up. And they're whacked at our GPS receivers, northern hemisphere, southern hemisphere. Now, if you're driving the road, down the road, relying on your TomTom or your Garmin, and it's not working for 10 minutes, no big deal. You'll get past it. But if you're landing a plane in a 200-foot ceiling and a quarter-of-a-mile visibility with a crosswind in Juneau, and you're relying on GPS, and it's gone for a couple of minutes, you got a big, big problem. So the FAA and many others recognize that. So we recognize that this threat of space weather to GPS, so we'll always have redundancy set in on some of those critical decisions like aviation. And this was just a report that came in from the GPS Operations Center in Schriever Air Force Base in Colorado, just kind of verifying. I always like to show that these are the words not from Bill Murtagh in the Space Weather Center, but from the users, the people that rely on this information. And they said at 1930 Zulu, UTC, widespread loss of GPS in the mountain states, specifically around the Four Corners. Aircraft were tracking 6, 7, 8 GPS satellites like they're supposed to. Within seconds, they were down to 0 or 1. Big solar radiation storms occur, and when they occur, if you're flying from the United States to Asia, what's the best route, or the typical route these days? Polar. You go right over the North Pole. From point A to point B is the quickest way. With the aircraft we have now, they can fly that long. Their biggest concern, there's no thunderstorms, or tropical weather, obviously, or anything like that in the North Pole. What they're concerned about is space weather. It will impact communication systems, it'll impact the navigation systems, and that little controversial piece, it also creates a biological threat, increased radiation exposure. The airlines don't want to deal with it. As soon as they get the warning from the Space Weather Prediction Center, they say, okay, we're not going polar. We're going to avoid it. Last year was 11,300 flights that flew polar, 13 major airlines. Those folks they'll start rerouting as soon as these space weather events occur. So I'm just going to finish up just showing, go ahead and click on that, Dana, and I mentioned it earlier, when we get a coronal mass ejection, a blast of material that shoots out into space, magnificent explosion, but it's got magnetic cloud. It just shot out a magnet, and that magnet is going to interact with the Earth's magnet, and we're going to have a storm. We'll issue a watch 2 days in advance sometimes to give people a heads up. It'll impact lots of different technology. But if John was here, this is where I would turn it over to him, Chuck, right? I'd say, John, give us the power grid. But the bottom line is this. I can give you the takeaway without the technology and the better explanation John would give. The bottom line is when the CME impacts the Earth's magnetic field, we're going to have a reaction. There's going to be currents, electrical currents developed in our magnetosphere and ionosphere. They will manifest themselves right on Earth. We'll have current induced on the ground that's going to find its way off and into big conductors like the power grid, pipelines, railway lines and whatnot. And the bad news is this, folks, and it's the news there you'll see in that bottom yellow box. Perhaps the most vulnerable place in the world is the United States, the northeastern part of the North American continent. We have all the ingredients. We have a very intricate power grid that acts like a big antenna. Obviously, we need that. We have the higher latitudes. The geology is critical, how the current will flow through different types of rock formations. Our position relative to another big conductor, salt water, the ocean, all come into play. In the recent Lloyd's report, Chuck, remember it said that the most vulnerable location in North America was the corridor between Washington, D.C. and New York City. Not what you want to hear. That is the reality, though, and we recognize, even with the moderate storms we get, that indeed it's those locations that do get impacted. The nuclear power plants in New Jersey and Pennsylvania and up in New England get impacted regularly. Manageable. We just hope it is during the big one. Thank you very much.
Thank you, Bill. As Scott McBride comes forward, is there one question? And by the way, what we're going to do is we're going to go into Scott's presentation, and then after that, we're going to take like a 2-minute break so the folks from the cyber panel will be able to come up. Scott's group over at Idaho National Labs actually did groundbreaking research on live power grids that were actually in operation. He's going to tell you that. And he's going to give you a first public release of Defense Department research on this topic this morning. Okay, so this is going to be very interesting for you. One question for, is Bill still here? One question in the front rows, really fast for Bill? We have one question. Okay, go ahead. Identify yourself and ask your question for Bill.
Meg Abraham, and I've worked extensively on the satellites that track this, and I wanted to know, so we've got, you know, the GOES system, for instance, that gives us a lot of early warning. How much warning are you able to then translate out to government entities? I know that the satellite doesn't get the information instantly either, so there's a stepped or time delay.
Right, there's two pieces to that. When with that coronagraph that shows the material erupting from the sun, fortunately, that's the stuff that causes the geomagnetic storm, and there's several different types of space weather. That's the biggest, the most critical one, and that's the one we get the most lead time on, because that's the stuff as it erupts from the sun. Unlike some of the other material, is moving slow. It's only moving about 5 million miles an hour. It's all relative, but that's actually making a 93 million mile transit. That's pretty slow. So we can give the power grid first heads up, first forecast, first warning, sometimes 15, 20, or even 50 hours in advance. But then we've got, and I didn't highlight this, we've got that L1 satellite. It sits at L1 is the Lagrange orbit, which is 1 million miles out into space along towards the sun. So we've got this buoy out there, kind of like a buoy off of the shore of Miami, and when the hurricane hits it, we get our first readings. That's our first readings. If that CME hits that spacecraft, now I know, now I'm dissecting it. I know what the density is, the temperature, the speed, and the magnetic field. So now can issue an imminent warning, because it's going to be here in about 20 minutes or 30 minutes. So that would be the process. So there's degrees of lead time. Of course, the accuracy would be another story we can talk about separately.